Okay, good afternoon, everybody. So, confidence intervals. We said point estimations are not always good choices for estimating a parameter of a population. Why? Because the probability of finding the actual mu of the population using one value of x bar is equal to 0. Okay? For example, for normal distribution. That's why we said, okay, how about combine what we learned in sampling distribution, which is the distribution of the point estimator, and also the point estimation properties, combine them together and find an interval that includes your actual parameter with some confidence level. That confidence level we call 1 minus alpha. And these two limits or bounds are basically two separate functions of random variables. As you can see, L is g of x1 to xn, and u is h of x1 to xn. We started with basically a simple case when we have a normal distribution and we want to find the confidence interval, 1 minus alpha % confidence interval for mean of this normal population. Variance is known, so we know the value of variance. And we show that in this case, x bar follows a normal distribution with this mean and variance. Therefore, I can standardize that, and I can use the property of standard normal distribution or z distribution and say, okay, I want to have 1 minus alpha in between. Therefore, I can basically do some calculations and find upper and lower confidence interval. Okay, we did these calculations, I think, last week. And we said this confidence interval can be used for non-normal distribution, but when your sample size is very large, in this case, n greater than 30. And basically, your sigma is known, any sample size is known, x bar is the average of your random observation or random sample, and z alpha over 2, you can find it from table. That's it. We had one example, and then we explained what is the interpretation of the confidence interval. Basically, what we do, we say if we collect a sample from the population, then from this sample I can get one x bar, and based on that I can find a confidence, lower and upper confidence interval. If I repeat this so many times, another sample, I get another x bar. These x bar are different because these are random samples. So this is 10 parts, this is another 10 parts. So x bars are different, therefore your confidence interval would be different. And if I do it for so many times, then some of these confidence intervals include the actual mu. Some of them, as you can see, some of them like this don't. Okay? So on average, I would say, let's say the confidence level is 95%. On average, I would say 95% of those confidence intervals include the actual value of mu. That's the interpretation of confidence interval. Does it make sense? Any questions? Where's this guy?
Do they all have to be of sample size then?
Not really. But yeah, not really. They can have different sample sizes. Yeah. Any other questions? Okay. So we had the choice of sample size, and we said, okay, if we define error of estimation, which is the actual mu minus x bar in terms of absolute value, then we can find n as a function of the amount of error we expect to get. Okay? And so this is the one way in practice that you can find a good sample size when you are doing a statistical inference. Okay? we had one example for that, and we said, what if we want to have one-sided confidence interval? For some cases, for example, if we care only about the upper limit, let's say we care about maximum waiting time. Okay, we don't care. The lower the better. So we want to have an upper bound. Or in some cases, we care about strength. Strength, the higher the better. So we don't care about we care about the lower bound, not upper bound. So in this case, we have one-sided confidence interval, and it's very similar to two-sided. We just replace alpha over 2 with alpha here. Okay, because we push all alphas here in this case, you can see we have alpha over 2 here, alpha over 2 here. We push all of them into one side, and we get lower and upper, basically, confidence interval. Is it clear? Any questions? Okay. Again, it can be used when n is greater than 30. Did I go through this example in class? You remember? I did? Okay. So we had this example. Yes, I remember now. And this is the way that we use table. Now, let's talk about the case that we have a normal distribution and neither mu nor sigma is known. Okay? So what we can do, we can say, okay, I have a random sample. From this random sample, I can get X bar, and I can calculate S. Then in this case, the distribution of X bar minus mu divided by the standard error, estimation of a standard error, which is S divided by square root of n. This is what? You remember T with n minus 1 degrees of freedom. So very, very similar procedure. We just replace Z with T. Okay, T n minus 1 degrees of freedom. And this is the lower and upper confidence interval that we get. So at the end of the day, we get mu is between X bar minus T alpha over 2 and n minus 1 degrees of freedom. This is for the lower bound, and for the upper bound is the same thing with a positive number. Okay? That's it. If you want to show how it is derived, just follow similar step as Z distribution. And since we are using S instead of sigma, we are replacing Z with T distribution. Okay? Then do the same calculation. Very same calculations. Okay. So what happens if n is greater than 30? That actually was one of the questions in your exam. You ended up with T with 99. I should not say that. Yeah. Okay. So, never mind. Anyways, when n is greater than 30, you can use Z instead of T. Okay? Let's move on. So one example is so one example is this. As you can see, we have a test, some alloy specimens, and we tested tensile adhesion. Basically, we measure the tensile adhesion. Then we have actually how many? 22 specimens, and we want to find the confidence interval, two-sided confidence interval for the mean of tensile adhesion. Okay, so X bar is given is 13.71, and S is given as 3.55. We can easily use the equation that we had before. Let me just write down X bar 13.71 and S 3.55. Just plug it in. So it's going to be 13.71 minus NT. Alpha we assumed is 0.05 because 1 minus alpha is 95%. So T of 0.05 and n minus 1 degrees of freedom, which is 22 minus 1. We need to find this guy from table. Let me see if I have table here. Yes. So alpha is 0.05, degrees of freedom is 21. Number is this. Okay? 1.721. So it's 1.721. Okay? Just replace it here. Oh, actually I made a mistake. What? It should be divided by 2. Okay? Because alpha is this guy. I'm looking for T of alpha over 2. As you can see, this equation, T alpha over 2, which is 0.025, is this guy. And for 21 degrees of freedom is 2.08. 2.08. Okay, so it's 2.08. If I go back to equation, you can see the equation. S is 3.55 divided by a square root of 22. This is for the lower bound, and upper bound is the same thing. With a positive sign. Okay? Easily. Let me see if I have the numbers here in this example. Should be somewhere here. Yes. 12.14 is this guy, and 15.28 is the other one. Okay? Yeah, go ahead.
Is this ever defined in fractions of mu rather than with actual numbers? So like, if you wanted to be like the lower bound be like 10% less than mu, and you want the upper bound to be 10% more than mu, does that make sense?
So I'm thinking if I have seen anything like that before. For engineering purposes, they do something like that, but that one is not for confidence interval. This is more sort of like a specification limit, which is different from confidence interval. So those are sort of like engineering specification limits. That's different. Yeah. No, I've not seen anything like that, like 10% of mu. No. Any other questions? Go ahead.
I wondered for this example if tensile adhesion, if you cared if that was too large. I'm not sure at the value.
Oh, the value is too large for that?
In the sense that if it's better to do it one-sided.
Oh, I see. Yes. So it depends. Yeah. Tensile sometimes higher the better. You want to do like a one-sided, but sometimes you just want to feel what would be the actual mu. So your actual mu would be between these two numbers. That's the difference. Okay? Any other questions? Okay. What if you're interested in one-sided? That's, again, is easy. You just replace alpha with alpha over 2 with alpha. And as you can see, when n is large, you can approximate t with z. Okay. So this example, we are interested in one-sided. I think that's the same example. We want to say 95% confidence interval. I think that's back to your point, because it's tensile adhesion. We want higher the better, so we want to have lower bound for that. Okay. And And that's easy again. We find this t based on new alpha, because alpha is not alpha over 2 anymore. It's 0.05. And then we just plug it in here, and then we get the lower bound, which is, as you can see, is a little bit higher than this guy. Why? Because our alpha is not 0.025, it's 0.05. Okay? Which pushes the confidence interval a little bit to the right side. Any questions? Is it clear? Now you can see how easy is this material compared to estimation and sampling distribution. But actually, you needed to know what sampling distribution is, what estimation is. Now, I'm sure that some of you have seen this before, even used it, but now you can understand what is behind that. You know, why are we doing this, basically, are using these confidence intervals? Okay, for chi-square distribution, it's a little bit different. In a case that we have, again, a normal population, and we want to find a confidence interval for variance, not mean. Okay? So what we do, we take a sample, we calculate S squared, and we know that n minus 1 S squared divided by sigma squared follows a chi-square distribution with n minus 1 degrees of freedom. Okay? And I think I have, yes, chi-square distribution here, so it's not symmetric. I want to have alpha over 2 here and alpha over 2 here. So what is this guy? Is chi-squared alpha over 2 with n minus 1 degrees of freedom. Why? Because it's the point that probability after this point is alpha over 2. Can you tell me what is this guy? Is the point that probability after this point is what? 1 minus alpha over 2. So it's chi-square of 1 minus alpha over 2 and minus 1 degrees of freedom. Okay? Why? Because probability after this point, which is this area, is 1 minus alpha over 2. Because before that is alpha over 2, after that is 1 minus alpha over 2. So I show this with chi-square 1 minus alpha over 2 and n minus 1 degrees of freedom. Does it make sense? Yep.
So in the figure here, it has alpha, but is that...
No, this is just to show what do I mean by chi-square alpha and k. That's it. So this is the actual figure I'm going to use to derive those confidence intervals. Let's get rid of this. Stop getting confusion. Okay. So what I'm going to do, I'm going to say probability of chi-square n minus 1 degrees of freedom between these two numbers, which is chi-square of 1 minus alpha over 2n minus 1 degrees of freedom, and chi-square of alpha over 2n minus 1 degrees of freedom. This is 1 minus alpha. So probability in between is 1 minus alpha. Okay? And I know this guy is this. So n minus 1 S squared sigma squared between these two numbers. This is 1 minus alpha. And then what you need to do, you just need to reverse the fraction multiplied by a squared. I'm going to do some calculations and manipulation here to keep sigma squared in between, okay, by reverse the fractions and multiply it by n minus 1 s squared. So if I do that, I need to change the sign of inequality, and I get this guy at the end of the day. So this is the lower bound. This is the upper bound, as you can see. Okay? Here, upper bound and lower bound. By the way, it doesn't really matter if we use equality or a strict inequality. Why? Because the point probabilities are equal to 0 for continuous distributions. Any questions? We good? For one-sided, upper bound, just replace alpha over 2 with alpha, as you can see. For the lower bound, the same thing. Just replace alpha over 2 with alpha. That's it. So SS squared is given. You have a sample. You can calculate SS squared. N is the sample size. And this guy, you can find it from the chart or table. One example here. So we have a filling machine for liquid detergent. We want to see what is the filling volume, the fill volume. So we collect a random sample of 20 bottles, okay? And then measure the fill volume. And the variance of those measurements is 0.0153, okay? Then we want to see, we want to find basically a confidence interval. And in this case, we are using an upper, basically, confidence interval. So your sigma squared, I'm using alpha equal to 0.05. So it's upper confidence interval. So chi-squared of 1 minus 95%. I'm sorry, 1 minus 5%, which is 95%. And n is 20, and minus 1 is 19. I can find it here from table. So 95 is here, and degrees of freedom is 19, which is 10.12. 10.12, that's the number. Okay? N is 20, and S squared is this guy. So I can easily find the upper bound. So this is the upper bound for variance. For a standard deviation, I can just simply take a square root. That's it. Okay? And this is basically the upper bound for 0.70. Do you know why we got upper bound in this case, not lower bound? No, because we are not talking about the mean. Overfill and underfill means like mean.
We don't want too much difference in how the bottles are filled.
So the variance means it could be overfill or underfill. Okay? So the variance is deviation from mean. Am I right? So we don't want to for the variance to be large. Okay? That's why we define an upper limit for that rather than lower limit. The lower, the better. Okay? Does it make sense? Okay, good. So last type of confidence interval for one population is Bernoulli population. For Bernoulli population, we have one parameter. And the parameter is basically P, which is the percentage of success, and it depends on how you define success. You can define success as producing a non-conforming part. You can define success as basically being a woman in a population. You can define basically as a percentage of vote to a specific candidate, you know. So you have one parameter called P. So you get a random sample, and this random sample are 0 and 1s, okay? X1 is 0, 1, X2, 0, 1, and so on and so forth. Okay? Then what is the point estimator? You've seen this before, is X bar. That's the MLE estimator. So the question is, what is the distribution of this X bar? Okay, but let me ask you this question first. So what is distribution of this guy? I don't know if I asked this before, but let's see who can answer. So what is the distribution of summation of xi's? What? What is the distribution of xi? Let's start with that. Individual xi. What? Bernoulli. So what is the summation? Binomial. What is the distribution of x bar? Why? So the distribution of x bar is not really known, but we can approximate it with normal when we have large n's. Okay? So x bar approximately follows a normal distribution with the mean, which is p, and the variance, which is p1 minus p divided by n. Okay? Is it clear? So I can say my p hat, which is x bar, minus p divided by a standard deviation, follows what? A z distribution which is normal with 0 and 1. Okay? So this guy is z. Then I can use normal, basically distribution, the finding confidence interval for normal, mean of normal distribution with known variance for that. Okay? Which is what? You remember it was x bar minus so what I'm doing, instead of x bar, I'm using p. Instead of a standard error, I'm using this standard error. And z alpha is going to stay the same. And this is for p. This is population percentage. This is random sample percentage. P hat is a random sample. This is for population. And then this would be for upper bound. Okay? Any questions? Is it clear? So I'm using the same, basically, confidence interval that I use for the mean of normal distribution. Remember that? Any questions?
This is kind of going back to one tail versus two tail.
Mm-hmm.
If I had some engineering problem where I didn't know before I did the analysis whether I only cared about the upper bound or lower bound, so I just did a two tail, and then it turned out that I actually only cared about the upper bound. In a sense, I would have to redo the analysis with a different alpha, right? So
Yes.
Is there ever a case where people just have alpha being 0.05 on both because they don't know before the problem if it's only upper? Does that make sense?
Yeah, I know what you mean, but I wouldn't recommend it because it's easy to calculate one more time. You know what I mean? You have the data, you have X bar and S, you just calculate that. When you reduce alpha, I mean, you are increasing alpha, you're reducing your confidence. Because confidence is 95%. If you're using alpha, like each side 0.05, you're reducing your confidence from 95 to 90%, which is not good. Okay, one thing here. So you can see the standard deviation or standard error depends on P, which is the mean of the process. You see that? This is not true for normal case. But what I did, I just replaced P with P hat. Okay? So I estimated basically based on the sample that I have. So it's not truly a case that I have confidence interval for mean of normal distribution with known variance. It's the case that I'm estimating the variance. Okay? So it should be what? T, am I right? But I'm using Z. Do you know why? Because the sample size is large, that's it. So actually it's T, but I'm using Z because the sample size is large and the T and Z are going to be the same. Okay? Yeah. Yes, yes. So let's say you are talking about, let me see, the percentage of non-conforming items in a population. Okay, so you have a lot of parts, like 10,000 of them, okay, or million of them, and you want to see what is the proportion of non-conforming parts. Then what you do, you randomly sample 10 of them, or not 10 is a small, 100 of them, okay? Based on that, you can find how many of them are non-conforming. So your p hat is number of non-conforming divided by 100. Then you use this information to find a confidence interval for this guy, for the actual. And another case is, for example, an election. Okay, you want to see what is the percentage of population voting for some candidate. Okay, for one specific candidate. What you do, you collect a sample. You ask them who voted for did they vote for that guy or that candidate? Then you can estimate p hat based on that sample and estimate and have a confidence interval for the whole population. Does it make sense? No. That's the proportion. It should be between 0 and 1. Okay? So it's a probability. Okay. So one example. In a random sample of 85 automobile engine, crankshaft actually, bearings. Okay? So we have 10 out of 85 has a problem with the finishing. So they have rougher surface. And the point estimate for that is 10 divided by 85, which is 0.12. So we want to have a two-sided confidence interval. So based on 85, I get 10 divided by 85. This guy was 0.12. Then I just plug in the numbers here. Alpha, we assume, is 0.05. So alpha over 2 is 0.025. So Z alpha over 2 from table is 196, let's say. 196, yeah. So 1.96 times 0.12, 1 minus 0.12 divided by n, which is 85 in this case. And the upper bound is the same thing. With the positive sign. Let me see if I have here. It's 0.05. 0.05 and 19%. Okay. So what does it mean? That's a good example, actually. The actual, I can say with a confidence of, let's say, 95%, the actual proportion of non-conforming parts in this process is between these two numbers, 0.05 and 0.19. Okay? And you can see it's a little bit wide, basically, range, because it ranges from 0.05 to 0.19. Okay? So how can I have a more precise, by precise I mean tighter bound? Any ideas? How can I get it? Go ahead. Take more samples, definitely. So one way to do that, so there are two ways. So if I want to have tighter, okay, either I need to change alpha, okay, so which means I'm playing with my confidence, which is not a good thing. I want to keep my confidence high, okay, because if I increase alpha, what's going to happen? If I increase alpha, this is normal distribution. This is alpha over 2. This is Z alpha over 2. If I increase alpha, then Z alpha over 2 decreases, okay? Because it shifts to the left. So I'm decreasing this guy. Decreasing this guy means I have tighter bounds. This is not good because at the same time I'm changing my confidence. I want to keep my confidence at 95% and get a more precise, basically, confidence interval, and I can do it by increasing n. When you increase n, which is a sample size, you can see this is in the denominator, then this guy decreases, therefore and also this guy. Okay? Therefore your bound confidence interval is tighter compared to the smaller ends. That's true for any confidence interval. As you can see here, this is true for here and this guy. Okay. Any questions? We good? Okay. Now, sample size for the case of Bernoulli. Do you remember, based on the error of estimation? Error of estimation in this case would be what? Is this guy. That's the error of estimation. So your point estimate and the actual parameter, how much they are different. Okay? And so if you remember, for normal case and mean of basically normal distribution, this quantity was this guy. Okay? Now I'm replacing sigma squared with P 1 minus P. Is it clear? That's the same basically story. I'm just replacing sigma squared with P1 minus P, which is the variance of what? A Bernoulli distribution. Okay? Go ahead. Exactly. That was my question you asked. So you don't know P. Okay? Here you don't know P. So some people say, okay, you may start with a smaller sample and get the estimate for that, and then replace P with P hat. So let's say you start with 10 sample or 20 sample, or sample size, a sample with size of 20. You get an estimate for P hat, and you replace P with P hat, and then you can actually calculate the n value. Okay? So let's say you start with n20. You get a P hat, use P hat in this equation, and then you get your actual n50. So what does it mean? Get 30 more samples, combine with that and test and re-estimate your P. Does it make sense? Okay? That's one way. again, the question is, we don't know P because this is population. And N depends on that. So what I can do, I can start with the small p first, have a rough estimate, okay? Then use that one to find the actual N and replace, I mean, like if the actual N is like 50, then I need to get 30 more samples or 30 more observations. That's one way. Another way is to be more conservative and find P that maximizes your N, okay? So this guy, P times 1 minus P, is what? Is a quadratic function, okay? So this guy is a quadratic function. And let's say this is constant. This is constant times a quadratic function. So if I want to show it, so it should be something like that. Okay? And it's maximized when P is equal to what? 0.5. Okay? And 0.5 means 0.5 times 0.5, 0.25. So you replace P times 1 minus P by 0.25. Okay? Again, that's the second approach. I don't know the value of P. So that's the equation. I don't know the value of P. Why? Because this is the population percentage. But I'm going to be conservative. I want to find P which maximizes N. So I'm plotting N as a function of P. This is constant, and this is a quadratic function, which is in this form. The maximum happens in 0.5. If P is 0.5, it's 0.5 times 1 minus 0.5, which is 0.25. And that's what you get. Any questions? We good? That's one example. It says based on some initial estimates, we know that P is 0.12. And then we can find N based on that. Alpha is 0.05. This is the alpha over 2. This is the error. Error we want to be less than 0.05. And if we do the math, it's 163. Okay? If we do not use this initial estimate, what I'm going to do, I'm going to use basically 0.25 instead of this guy as a variance because it maximizes N, and your N is 385. And as you can see, definitely this guy gives you a tighter confidence interval compared to 163. Is it clear? Any questions? Okay, for one-sided, you can just see, replace alpha over 2 with alpha, lower side and upper side. That's easy. And that's, I think, the last slide. What if, so right now I covered Bernoulli distribution and normal distribution. What if I have any distributions, like geometric or Poisson? So what should I do? Okay. For this case, I can use basically a very nice property of MLE, if you remember. So MLE, when n increases, it follows a normal distribution. Okay? And then I can use this property to come up with a confidence interval. Let's say I have a general distribution with parameter theta, and the MLE estimate is theta hat, and I have large sample. Then I can argue that theta hat is approximately normal distributed with this mean, which is the actual parameter, and the variance of theta hat. Then I can define this guy as standard normal distribution, and I can use this confidence interval. Okay? Let me give you one example for Poisson. I know that some of you have exam, so if you want to leave, feel free to leave. I'm going to repeat that one later again. So X follows a Poisson distribution with parameter lambda. Okay? So the question says, I want to find a 95% confidence interval for this lambda based on a random sample. Okay? Population, lambda, random sample. So first of all, I need to find the MLE estimate for Poisson. Okay? So what is the PDF for Poisson distribution? That's the PDF. Okay? And what is the likelihood? Random sample. Or log likelihood, basically, would be better. It's the summation of log of your PDFs. Okay, in this case is log of the first term, which is this guy, log and exponential, they cancel out each other, plus log of the second term, which is x log of lambda, and minus log of the third term. And this is xi. Summation I from 1 to n. Okay? So that's log L. What is the next step? Take a derivative with respect to lambda. If I do that, this is going to be -1. This guy is xi divided by lambda. And this guy goes away because it has nothing to do with lambda. And if I solve this for lambda, at the end of the day, I get lambda hat equal to x bar. That's the MLE estimate. So the MLE estimate for Poisson parameter is x bar. Okay? That's the first step. So I got my MLE estimator, maximum likelihood estimator, which is x bar. Now, what else I need to know? I need to know this guy, which is the variance or standard deviation of my estimator. Okay? So what is variance of x bar? You remember? Sigma squared divided by n, which is variance of x divided by n. Do you remember what is variance of a Poisson distribution? Lambda, exactly. So for Poisson distribution, expected value and variance both are the same, equal to lambda. So this is lambda divided by n. Okay? So I can say my confidence interval is point estimator, z alpha, standard error. So point estimator x bar, z alpha. The standard error is lambda divided by n. I need to estimate that. So the estimate of this guy would be just replacing lambda with x bar. Okay? And x bar minus plus z alpha over 2 x bar divided by n. So this is the variance. I'm sorry, I need to take a square root because this is the variance. Let me just write it here. Your standard error of x bar is this guy. So the MLE estimate of a standard error, standard deviation of x bar is x bar divided by n. This is what I used here and here. Okay? Any questions? Is it clear? For any distribution, you can do that. Again, I'm using an estimate. Therefore, it should be t. But since we are talking about large samples, I replace t with z.
So before we use the t-distribution to calculate for sigma squared for the variance?
Yes. If the variance is unknown, yes.
Right. Could
Yeah.
we do this method for sigma squared as well? Or no? Could we come up
For
with
the
it?
confidence interval for
Yeah,
sigma squared?
yeah.
Actually, we use chi-square for confidence interval for sigma squared.
yeah.
Yeah. But this one, I'm not. That's actually a good point, because the mean and variance are the same. You want to see if.
Could we like make an MLE for variance and then this apply or no?
It's actually a good question. So what you need to do, so he's asking, because the mean and variance are the same, I used basically this guy to find the confidence interval. I used X bar to find the confidence interval. He says, can I use maybe S squared? Because I know that n minus 1 S squared divided by sigma squared follows a chi-square distribution. Is this that you're asking or not?
No, I was just asking if we wanted to get a confidence interval for variance.
Variance of Poisson distribution or variance in general?
Just variance in general.
Oh, okay. Sorry.
Yeah. Could we use this fact as well or no?
So yes, we can. So here is the point. The variance for normal distribution is independent from me. Okay? For almost all other distributions, your variance and mean are functions of the parameters of your distribution. For example, for Poisson, mean and variance are functions of lambda. For exponential distributions, your mean is this guy, and your variance is this guy. As you can see, both of them are functions of your parameter. So what you do, you find a confidence interval for the parameter, and if you want, you can use this equation to make it a confidence interval for your variance. Okay? For example, if you get the confidence interval for lambda for exponential distribution, then you can reverse it, square that to get a confidence interval for variance. But always start with a confidence interval for the original parameter. Does it make sense? That was a good question. Any other questions? Good? See you on Friday. As a matter of fact, maybe I